Let us switch over to problem number 11. Let me read it out. A long solenoid has 200 turns per centimeter and carries a current I. The magnetic field at its center is 6.28 into 10 power minus 2 Weber per meter square. Another long solenoid has 100 turns per centimeter and it carries a current I by 3. That's 1/3 of the original value, what of course the earlier one is carrying. The value of the magnetic field at its center is how much? That is the concept. And of course this was a question given in IIT-JEE, that was in 2006. And the options are given this way. The first option is 1.05 into 10 power minus 4 Weber per meter square. The second option is again 1.05 but into 10 power minus 2 Weber per meter square. The third option 1.05 into 10 power minus 5 Weber per meter square. Fourth option is again 1.05 but into 10 power minus 3 Weber per meter square. The correct option for this particular question is B. That's 1.05 into 10 power minus 2 Weber per meter square or Tesla. So what exactly the concept he has given? It is based on a solenoid. Solenoid of course is going to have the magnetic field inside with a formula mu naught Ni. That all of you can understand straight away that N gives you the number of turns per centimeter length. In this case of course per centimeter length he has given. Sometimes they used to give per meter. But what exactly N is, if you look at, that's the number of turns per unit length. That's what we generally take it as N. So what is the formula for this magnetic induction inside the solenoid? It's mu naught Ni. N being number of turns, right, per unit length. That actually is the point we have to understand. So since mu naught being constant here, you can directly write that B is proportional to N into I. That is the ultimate equation we have to remember. So from which I can directly write B1 over B2 is equal to N1 over N2 into I1 over I2. That is the equation what we can write from this relation. Now what are the values he is giving us? You look at the magnetic field inside the first solenoid that has been mentioned as 6.28 into 10 power minus 2. So let us write in place of B1 that value 6.28 into 10 power minus 2. I in fact require the value of B2. Fine. How many number of turns we have per unit length in the first solenoid? It's given 200, and whereas in the second one it's given 100. So we can directly write here this N1 is 200 and N2 is 100 now into what amount of current that the first solenoid was carrying. He gave that one as I. So straight away I can write I1 as I. And what is I2? He said 1/3 of the current that has been carried by the first one. So you can directly write this one as I over 3. So directly you can cut this one, 3 going up, it becomes now 6. So what will now be the value of B2? That is the question. 6.28 into 10 power minus 2 whole divided by 6. You now will be getting around, that is nearby like 1.05 into 10 power minus 2 Weber per meter square. This actually is the value what we can expect directly. Had it been 30, would have got directly 5. Nearly, I am just writing. Since the options are also given in the same order, we now can identify what is the correct option out of the 4. It is the second option which is coinciding with the calculated value what we have got here. It's 1.05 into 10 to the power minus 2 Weber per meter square as such. So the answer for this particular question, we can write that one as B. That is the concept. So only thing you need to recollect from this one is what is that value of N. Only thing is sometimes of course he may give in one solenoid the number of turns per unit centimeter, in the other solenoid the number of turns per unit meter. So in such cases we just have to convert them, otherwise there is no such complication in such model question as such, which has been given in 2006 in EEE paper. So these models are very important for you to remember in this case. This is question number 11 what we have. Let us check the next number, that's problem 12, which is based on two straight current carrying parallel conductors like two long conductors separated by a distance d carry currents I1 and I2 in the same direction. The moment you just complete reading this first part of the problem, immediately you should get to your mind, whenever current directions are same in two parallel straight current carrying conductors, there will be attraction between those two conductors. I repeat, whenever the directions of currents in parallel conductors separated by a certain distance is same, the directions are same, then you can come to a conclusion there will be a sort of an attraction between those two conductors. That force, of course, we have a formula to calculate. All those things we shall discuss. Let us continue the problem. They exert a force F on each other. So definitely that F must be the force of attraction. Remember that concept. Come to the next. Now the current in one of them increased to 2 times. 2 times what? The initial value. It's understood. And its direction is reversed. The moment directions are opposite, there will be repulsion between those two conductors. So now earlier force of attraction what was existing between those two parallel conductors now will be converted into force of repulsion. That is one point one should understand first. And what else he is talking? The distance is also increased to 3d. Earlier the distance was d between them, now it has been made 3d. Then what is the new value of the force between them? That is the concept. So one should understand straight away, this particular question is based on the force between two parallel straight current carrying conductors. Right. And second point you should understand is the moment directions of currents in those two parallel conductors, they are same, then there will be attraction between them. And that force of attraction, we have a formula like mu naught by 2 pi I1 I2 L by d, the distance of separation between them. And of course the moment current directions are reversed, automatically that force of attraction which was existing between them earlier will now be converted or changed into force of repulsion. That's what he is talking. And the same problem has appeared earlier in EEE paper of 2004. Now let us check those options given. The very first option is minus 2f. And the second option is f by 3. The third option is minus 2f by 3 and fourth option is minus f by 3. Okay, now one thing you should understand here is why he is giving negative values over there in options. That means if you take attraction as a positive, the repulsion will be opposite by direction. Therefore, we can write that one negative. But usually we take repulsion positive and attraction negative, whatever it is the case, hardly that matters. When you are talking about one particular direction positive, the opposite direction to that one can now be taken with a negative sign. That is the understanding you need to have here. Now look at the way we have to solve, and the correct option for this particular problem, let me give you first. It is C, which is minus 2f by 3. That is the correct option for us. Let us now check what he is talking about. There are two parallel straight current carrying conductors. They are carrying currents, say as I1 and I2. And he has mentioned these two are separated by certain distance d. You can understand straight away like that. And the force between these two, which is now the so-called force of attraction here, that is given as F. So I can now write first step F attraction between these two conductors. That's mu naught by 2 pi into this value of I1, I2. Let us say the length what we have to consider, effective length between which the force that is existing, that is taken as L, over the distance of separation between these two, that is given as a d. So that is actually the formula for force, which is given in the problem as F. That we can understand. Now he is talking about some variation or changes they have made in these two conductors and the currents in fact and the distance of separation. If you take now F repulsion, it should be taken. That now is equal to mu naught by 2 pi. What did he say? Current in one of the conductors is made 2 times. So let us say I1 is made 2 times. So 2I1. I2 as it is. Effective length on which the force is calculated is same. He did not mention any variation over there. Divided by the distance of separation, that also he has made that one as 3 times. So I should write that one as 3 times d here. So now what will you get in this particular case? It is 2/3 of mu naught by 2 pi I1 I2 L by the value of d. And is it not simply 2 by 3 times the value of F now? So our answer is 100% 2/3 of F. But he gave one option only, 2F by 3, that too with a negative sign. Reason now you can understand. The moment you are considering attraction force positive, then automatically the force of repulsion is to be considered as negative. Quite opposite by direction you are finding the force being a vector, you can give direction to that. Thereby the correct option now becomes 2F by 3 according to the values given over there in the options. So what is the correct answer for this particular problem now? The correct answer should be C out of the 4 different values. So only thing you should understand is when will they be attracted and when will they be repelled. If the directions of currents are same, there will be attraction between them. If at all the directions of currents are opposite, then there will be repulsion between those two straight parallel current carrying conductors as such. That is problem number 12 what has been given here. Let us shift over to the next number, that's problem number 13, which was given in 2003 EEE paper. One of the best models once again here, which is in fact related to the concept of magnetism there. A magnetic needle lying parallel to a magnetic field requires W units of work to turn it through 60 degrees. That means from the direction of its position of rest. Position of rest, of course, will be along the direction of the magnetic field. Magnet's directive property is that it should show, or it shows directly, the directions of north and south of Earth or of that magnetic field in which that magnet is directly being suspended. So you can certainly understand this point as the directive property of any type of a magnet, irrespective of its shape or size. Now here also, the magnet is lying parallel to a magnetic field. Obviously, that will take, or that comes to rest along the same direction of north and south of Earth, or of that magnetic field in which it has been suspended. We know that. Now he said it requires W units of work to turn it through 60 degrees from the direction of the field. To rotate the magnet by 60 degrees, we need to do a work equivalent to W units. That's what has been given there in the first sentence of that problem. Now what next? The torque needed to maintain the needle in this position will be how much? In fact, when you rotate the magnet by some angle and leave it, it once again goes back to normalcy. Once again it goes back to normalcy. Due to what? Due to the torque that is acting on the magnet to bring it back to its position of rest. But here, what is he asking? What torque that is required for this magnet to stay in this new position? New position of what? 60 degrees angle from the direction of the field. So what is that value of torque that it is needed? That is needed to maintain the needle in this position, the new position. What is that value he is asking you? Of course, he has given 4 options. Root 3 W, and second one is W, third one is root 3 by 2 times W, and fourth option is 2W, and correct option is the first one. It is root 3 times the work, that is W. That's the point. One should understand first of all what is the formula for work. What is the formula for work? In rotating a magnet from the direction of the magnetic field by an angle theta. 2 things we have to understand here. Where from we are rotating? From the direction of the magnetic field in which it was at rest earlier. And secondly, by what angle you are rotating it? By an angle of 60 degrees we are rotating that magnet there. So you can certainly understand in this case work done in rotating a magnet by an angle theta from the direction of the existing magnetic field. W is equal to mb cos theta. In fact, we all know that is the work in rotating the magnet by an angle theta from the direction of the magnetic field. That is the concept. So he has given us in this problem, since theta is 60 degrees, we can directly write W becomes mb by 2. That is the first observation what we can have from the given data. But what is the question he is asking? He is simply asking you to calculate torque that is needed to maintain the magnet or that needle in this position now, in the present position. That is understood. So you can directly write what is the formula for torque that is acting on a bar magnet or a magnetic needle, whatever it is. It is mb sin theta. That actually is the formula what you might have derived earlier also. So mb sin theta, that gives us the torque. You can now write what is this value of theta. So you can write this one MB sin 60, because it is supposed to be in the same position. That's what he is talking. So sin 60 degrees now becomes root 3 by 2. That is what actually we people can understand. Now root 3 by 2, when you write it, MB by 2 times root 3, I can rewrite the same by rearranging it like this. And what is MB by 2? Already we have taken it, that one as work. So we can now write this value as M, that is W root 3. That is the concept. Since MB by 2 is W, we now can write W root 3. That is the value of torque that is needed to keep the needle in this position as such. That only he has given in the options as root 3 times W as the first option over there. So straight away we can take up here the correct answer for this particular question as A. So I just repeat once again these two formulae. One is the amount of work needed in rotating a magnet or magnetic needle from the direction of the field by an angle theta. What is the formula for work done there? It is MB cos theta. Work being a scalar, we will be getting there MB cos theta. That is the formula. And what next? What is the formula for torque that is to be taken up? Torque is MB sin theta. So just by taking these two, you can estimate what is the relation between the torque and this amount of work that has been done. So in this particular case, torque is root 3 times the value of W. That is the very first option for us in problem number 13. Now the next number is one of the excellent models what we have. From once again 2007 IIT-JEE paper, we have taken this problem. This is one of the excellent models they have created. A long straight wire of radius A carries a steady current I. You should understand the point this way. Long straight conductor okay is a straight one, but he is giving radius, that must be radius of cross section there. That radius of cross section he has just given as A of that straight conductor, which is carrying a constant value of current or a steady value of current, that is I. Fine. The current is uniformly distributed across its cross section. The current is distributed 100% uniformly. That's what has been mentioned there. It's not non-uniform distribution. Remember, the ratio of the magnetic field at distances 2A and A by 2 is how much? 2A is outside the wire. A is the radius of cross section. 2A the distance we are talking. So certainly that distance that is mentioned there, it gives you an idea that the point is lying outside the conductor. And what is the next value given? A by 2. A being the radius of cross section, A by 2, that point lies inside the conductor. So two things we have to take up here. One is at a distance 2A and one is at a distance A by 2. What is the ratio of magnetic field at 2A distance and at A by 2 distance respectively? What is that ratio is the question. Now if you look at the options given, first option is 1/4, that is 1:4 ratio. Second option is given 4, that of course you can say 4:1 ratio. And third one is 1, that's 1:1. and fourth option is given 1 by 2, that's 1:2. Out of all the 4 options, straight away you can take the third option is the correct option. It's 1:1. Both the values are going to be the same. That's what we have to consider. So let us once again check what is the way we adopt, rather the method we adopt to solve this type of a model question. One of the good models, as I have already mentioned in the beginning itself. If you take yet 2a, that is the distance I am talking, I take the magnetic field as B1, which of course can be written directly as mu naught by 2 pi I by a, that is 2a. Actual formula is mu naught by 2 pi into I by r. That is the formula for magnetic induction at a point outside a straight current carrying conductor which is at a distance r from its general axis. That distance is given 2a here, therefore I can directly write this value as mu naught I divided by 4 pi a. This is the first value what I can expect from it. But the thing is, the second one, if you look at, point is not lying outside the conductor. It is inside the conductor. Then how can we go for that particular value? You can take directly the concept of B dl is equal to, that is integral B dl what we people used to take up, is equal to mu naught into I like. That is the concept by means of which we have to estimate what is that value. So integral B dl is equal to mu naught I, that's what actually we can take up. I repeat once again here, let us take integral B dot dl. That of course if I take this way, it's mu naught I. This integral B dot dl, of course, B dl cos theta, that cos theta being 1, in this case it is B into dl. So what I can write now? B integral dl is equal to mu naught into I. How to take this value of I now? If I consider current per unit area is I by pi a square. Now what is the present area when the distance is a by 2? What will be the area of that particular circle? You can say, is it not pi into a by 2 whole square? So I think all of you might have understood this one. A is the radius. Now the radius is a by 2. Then what will be the corresponding cross-sectional area there? Is it not pi into a by 2 whole square? So what I can now write in this case is, per unit area, this is the current. Now what is the area? Presently, we have pi into a by 2 whole square. For pi into a by 2 whole square area, what is the current that is passing across that cross section? I think this particular calculation is clear to all of you. I by area of cross section, it is a current per unit area of cross section. Now the present area of cross section is pi into a by 2 whole square. So for this much of area of cross section, how much current that is passing across? So when you talk about, this is the calculation. Out of that, of course, pi I can cancel. I can simplify that one later. This B, whatever we are talking about now, I take that one as B2. What is that B2 over there? You can understand. That is the magnetic induction at that particular distance which is given as A by 2 from the natural axis of that particular wire. So that is what actually we have to understand. And what about this integral dl now? It now can be taken as B2 into 2 pi r. So 2 pi into A by 2. This is now going to be mu naught into I into A square by 4 whole divided by A square. A square cancels. Now this 2 gets cancelled. What is now left over? Check this one. This implies B2 is equal to mu naught I we have in the numerator. 4 pi A, that comes into the denominator. Look at this particular calculation thoroughly. If you take up B integral B dot dl as mu naught I, taking this formula, B we are taking its value as B2, which is at a distance A by 2 from the natural axis. And dl integral, that value is 2 pi r, r being A by 2 now. And what is this I? There you should be careful enough. If the current per unit area of cross section is I by pi a square, for the present area of pi into A by 2 whole square, what is the corresponding current? Just multiplying these two, you will be getting this value, and B2 I again have got same value what I have got for B1. Look at now, B1 is already mu naught I by 4 pi a. Even B2 also I have got the same value mu naught I by 4 pi a only. Then what is the ratio? That is the question he is asking. So simply speaking, 1:1. So if you divide B1 by B2, you will be getting 1. That only is the option C what he has mentioned in the problem. So the correct option for this one is going to be C again. So answer will be C for this question. One of the best models. Generally, whenever we consider a straight conductor, distances are all going to be taken outside the conductor only every time. But in this particular model, he has taken one point at a cross section of A by 2, where A is actual radius of cross section of that wire or conductor. Its A by 2 distance means half of that distance he is considering. So one of the excellent model questions that has been given over there in 2007 IIT-JEE. So one of the best models, one has to remember thoroughly this type of a model. So that is problem number 14 for us. Now look at the problem number 15. This also is one of the excellent model questions. This was given in 2001 in IIT screening examination. A long straight wire along z-axis carries a current I in the negative z direction. The magnetic vector B bar at a point having coordinates x comma y in the z is equal to 0 plane is how much? So he is just giving us first of all the current that is passing across the conductor, that is a long straight conductor, that's a wire he is talking, is along negative z axis. Along negative z axis, that means immediately you should get your mind that the magnetic field will now be confined to xy plane. You can take this same left hand rule of Fleming like. When you talk about that, this current, the central finger, if it is pointing towards negative z axis, then you will be finding the other two fingers, one is giving negative x-axis over there, negative y-axis over there, and the other one is giving positive x-axis over here. So what we people should understand out of this, since the direction of current is along a negative z-axis, the magnetic vector will certainly be confined to xy plane. That is the first observation you should have from this problem. What are the four options mentioned over here? Look at the first option, mu naught I by 2 pi into yi minus xj by x square plus y square. The second option is mu naught I by 2 pi xi plus yj by x square plus y square. And third option is mu naught I by 2 pi into xi minus yj whole divided by x square plus y square. And fourth option is mu naught I by 4 pi xi minus yj divided by x square plus y square. First and foremost, you should understand that since, directly I write over here, since the current is along negative z-axis or z direction, B bar is confined to xy plane. xy plane. So what exactly the concept? Along x-axis when you take, the distance is going to be y. And along y-axis if you take, the distance is going to be x. So x coordinate now becomes y for it, and y coordinate now becomes x for it. If you can understand that logic, straight away you can back the answer for that. See the very first option, mu naught I by 2 pi yi minus xj whole divided by x square plus y square. That is actually the thing what has been given. So you can understand when x and y are the coordinates, what is the distance to that point which is diagonal across? Is it not x square plus y square under root? But r square we used to take, root goes off. So r square becomes now under root x square plus y square whole square, which now becomes x square plus y square. So only thing you should understand is along x axis, the distance whatever we used to measure, that will be y. To that point, from x axis, the distance to the point will be y. From y axis, the distance to the point will be x. Identify this logic. Enough. Then automatically you can come to this conclusion, this B bar, that is going to be mu naught I by 2 pi, direct value mu naught I by 2 pi into what? yi minus xj divided by x square plus y square. So I think this particular concept is clear to you all. From x direction, the distance to that point will be y. From y direction, the distance to that point will be x. And if you apply this left hand rule over there, that x direction is positive and y direction you will be getting negative. Enough. Directly you can attack that answer there. So this is actually the correct option for that, of which the answer is going to be A for us out of all the four. So this type of a question requires a bit of concentration there. Problem is not lengthy. You are not going to have the problem lengthier. Only point here you should understand is how much you have understood about the wording what has been provided to us. So otherwise problem is just like that. That's not a problem. It's a very simple one. IIT screening paper that has been given in 2001, the correct option for this one is A, the very first option over there. That is problem number 15 what we have. The next problem, that is problem number 16. A proton, a deuteron and an alpha particle having the same kinetic energy are moving in circular trajectories in a constant magnetic field. If Rp, Rd and R alpha denote the radii of trajectories of these particles respectively, then he is asking you the relation between all the three. First option he has given you as R alpha is equal to R proton, which is less than R deuteron. The second option is given this way: radius of the trajectory of alpha particle is greater than the radius of deuteron is greater than the radius of the trajectory of proton. Third option, R alpha is equal to Rd is greater than Rp. And fourth option is given this way, that is all the three trajectories, their radii are equal. That is Rp is equal to Rd is equal to R alpha, that has been given there. Now first and foremost you should all understand, it's a proton, first one. Deuteron, it is the isotopic form of hydrogen, 1H2 we people used to write, and alpha particle which is helium nucleus. So if you look at the very first particle over here, that is a proton, we now can write 1H1. 1 is going to be the atomic number and 1 is its mass number. Likewise, deuteron, it's 1H2, we write 2 units of mass it has got and 1 unit of charge. And third one is alpha particle, which is helium nucleus, helium 2,4 we people used to write, that 2 represents its charge, 2 units of charge, and 4 represents mass, 4 units of mass it has got. Now what did he say? They having same kinetic energy are moving in circular trajectories in a constant magnetic field. Every one of you can understand directly, whenever a charged particle is entering into a magnetic field normal to the direction of the field, that is making an angle 90 degrees to the direction of the field, then certainly it traces a circular path. So that means you can all understand now BQV, which is the so-called centripetal force caused by the magnetic field on the particle, that now must be equal to mv square by r, that is centrifugal force. So the centripetal force caused by the magnetic field and centrifugal force that is acting on the same particle, as long as these two are equal, there is no problem for the particle to continue its motion along the same curved track. Now in this particular case, 1v you can cancel it. Now what is left over? BQ is equal to mv by r, which can be written as p by r. Every one of us we know well, p being the linear momentum of the particle that has been taken. So linear momentum in turn can even be written as 2m into Ke. We in fact have a relation between kinetic energy and linear momentum. Kinetic energy is p square by 2m formula we have taken up. So now p becomes under root 2m into Ke whole divided by the radius. So what is he predicting here, you look at, and what are the things he has given? all the three particles having the same kinetic energy. So kinetic energy is constant. It is same for all the three. And anyhow this number is a constant, okay, forget. Same magnetic field they are entering into. That means even B also is constant there. Then look at the remaining variables R, M and charge Q. So I now can write directly R is proportional to root M by Q. This is the ultimate result or relation you people have to remember. The moment radius of the trajectory is proportional to square root of mass of the particle divided by the charge. That means it is proportional to mass, directly proportional to root under mass and inversely proportional to the charge. Now I just take for all the three different particles. What are the values? So I can write the very first one, R of proton is to R of deuteron is to R of alpha particle. Now I can rewrite the same this way, root of mass of proton by charge on proton is to root of mass of deuteron by charge on deuteron is to root over mass of alpha particle by charge on alpha particle. And we know pretty well mass of proton is of 1 unit, charge also is 1 unit, it becomes 1 over 1, it is 1. Now what about mass of deuteron? 2 units, whereas charge is only 1 unit. What about mass of alpha particle? Mass is 4 units and charge is 2 units. So what is it you are getting directly? It's 1 is to root 2 is to 1. Look at carefully, this one represents radius of the trajectory of proton. This one represents radius of the trajectory of alpha particle. So what are equal here now? You can directly say now radius of trajectory of proton is equal to radius of the trajectory of alpha particle. That's what is the result first. And both are less than the second one. Root 2 is 1.414. It's certainly more than these two values. Therefore, these two are numerically equal 1 and they are supposed to be less than the radius of the trajectory of deuteron as such. So this must be the correct result what we can expect from this ratio. So looking to all the 4 options what have been mentioned to us, you can identify the first option is the correct option for it. So the option 1, that of course is A, is the correct answer for this particular question. Now sometimes they used to give same momentum. Same momentum means okay, P will be constant, then R and Q are directly are inversely proportional to each other. Straight away you can write that. So this type of a rather problem is a very commonly asked model in different entrance examinations. So try to understand that this particular problem has been asked in 1997 IIT paper. So such models also have come earlier. So concentrate on these models as well. That is problem number 16 what we have. 17th problem is based on the concept of a galvanometer, that in fact conversion of voltmeter and other things like. A galvanometer of resistance 25 ohm having full scale deflection for a current of 10 milliampere is changed into a voltmeter of range 100 volt by connecting a resistance R in series with the galvanometer. What is the value of R? This was the question given in 2000 IIT paper. And the options are given this way. The very first option is 10,000 ohm. The second option is 10,025 ohm. And third option is 975 ohm. And fourth option is 9,975 ohm. In fact, the correct option for this particular problem is D, that is 9,975 ohm as such. First and foremost, you should come to this concept first. How to convert a galvanometer into a voltmeter? We connect a very high resistance in series to the galvanometer. Thereby, the entire system, including that high resistance connected across the to the galvanometer, that is now to be called as voltmeter. Suppose if it is to be converted into an ammeter like, recollect even that point also to mind. You need to connect a very low value of resistance in parallel to the galvanometer. So in this particular case, our answer of R is supposed to be very, very high. Of course, all the four options are given that way only. 10,000 ohm, 10,025, 975, 9,975. So certainly greater values only we can expect. What is the value of R, the question? You recollect once again the formula what you have discussed as far as voltmeter that is concerned. R must be V by Ig minus G. There is a direct formula. What is this value? I will remind you. In fact, when a galvanometer is connected to a high resistance R, this particular combination, we name that one as voltmeter. Now observe carefully, since these two are connected in series, what would be the effective resistance? G plus R. From that effective resistance, if I subtract G, the resistance of galvanometer, I get the resistance connected there in series, that is R. So what is the concept here we have to understand? From the effective resistance, if we subtract the resistance of the galvanometer, we get the value of R. It's fine. But how to calculate effective resistance? It is by the application of Ohm's law. V by I. In this condition, you people can understand directly current entering, if I take it as I, same current passes through the galvanometer, same amount of current that even passes through the resistance connected in series also. So whether I call it Ig, that is current across the galvanometer, or I call it IR, that is a current across the resistance, or simply I, that is the total current across the voltmeter, like, all the three are one and the same. Therefore, V by Ig, that gives you the effective resistance of this system, that minus G will now be the value of R. Now look at the values what he has mentioned. What should be the range of voltmeter he wants? A range of 100 volt, he said. So directly you can write 100 over here. Fine. What is the current across the galvanometer? He said it gives full scale deflection for a current of 10 milliampere. So straight away you take 10 milliampere, 10 power minus 3, minus the galvanometer resistance. It has been given as 25 ohm here. Now cut this one first. You will be getting this one 10,000 minus 25, which now becomes 9,975 ohm as such. So what resistance that is to be connected in series is the question. It is 9975 ohm that is to be connected in series to that galvanometer to convert that one into a voltmeter as such. So the correct answer what we have got here is tallying with the fourth option given there. Therefore, the answer for this question is going to be D. This is the one. This is question number 17. But suppose if it is a question on ammeter like, you used to get the resistance which is to be shunted there will be very less. You may be getting in points or you may be getting in single digits. Whereas in voltmeter, very high resistance is going to be connected. Therefore, we have got here 9975 ohm that is to be connected in series like. This is problem number 17, which is based on a voltmeter. Let us check the next number, that is problem number 18. Two thin long parallel wires separated by a distance B are carrying a current I ampere each. The magnitude of force per unit length exerted by one wire on the other is how much? In reality, one should understand a simple point out of this model. The problem is not a very lengthy one. Suppose if A repels B, then it is understood B also repels A equally. If I say A attracts B, then it is understood B also attracts A with the same value. So in fact, you people can understand in this particular case or the examples what I gave you just now, if you take one as action, the other one automatically will become the reaction. Both action and reaction, they act on two different bodies equally but in opposite ways. That is the concept what one has to understand. So based on that particular aspect, we just have given this problem. That means the magnitude of force per unit length, okay, exerted by one, that is one wire, on the other. Whether I say that is the force of attraction or repulsion between both the wires, or with what force one wire is attracting the other wire, or with what force one wire is repelling the other wire, whatever be the nature of the question, let them give. Our answer is going to be the same. So when once you take the force exerted by the first wire on the second as action, then the force exerted by the second wire on the first, that now becomes reaction. So the question has got four options once again. First option is mu naught I square by B square. The second option is mu naught I square by 2 pi into B. Third option, mu naught I by 2 pi into B. And fourth option, mu naught I by pi B square. These are the options given. Let us first of all check here two straight parallel current carrying conductors. They are now carrying the same amount of current. He did not mention whether they are in the same direction or in opposite directions. No worry. Because if the directions are same, the force will be attractive by nature. If the directions are opposite, force will be repulsive by nature. So you can say this is I, this is I. Let us now check the distance of separation between these two is of course D. Right. So what is the value he has given? You see, two thin long parallel wires separated by a distance B. So I can take that one as B here. What is now the force of attraction or repulsion between these two wires? That by formula we can write mu naught by 2 pi into I1 into I2 into L by the distance of separation as d. This is the formula one should recollect first. I1 is the current in the first conductor, I2 in the second, L is the effective length of both the conductors, which of course are experiencing a force between them, and d is the distance of separation between these two conductors as such. Now here what are the values he has provided? I write them. Mu naught by 2 pi, I1 into I2, that is I into I, into L by d. That d in this particular case is given as B. So what can we write now? Force per unit length I just want. Force per unit length, that is simply F by L. So what is now left over? Mu naught by 2 pi into I square by B. That must be your answer. So mu naught by 2 pi into I square by B, look at out of all the 4 different options, the second option is tallied with our calculated value. So mu naught I square by 2 pi into B, that is the answer. So the correct answer for this particular problem is simply B. But one thing more I just want to mention here. When a straight conductor, instead of giving you 2 conductors over here, sometimes they may give a straight conductor is just carrying some current I like this. And look to this concept also. Instead of giving both the conductors initially itself like this, he may say there is a straight conductor carrying a current I1 in one particular direction, which is horizontal by nature. There is one more conductor which has been placed below this one at a distance, say d, like that he may say. There is one conductor A which is of course carrying a current I1, it's horizontal now. There is another conductor B of which the length is given as L, is placed below this. At what distance? At a distance d. Now what this man says is, when the second conductor also is carrying some current, it is observed that the conductor B is in equilibrium. Understand this concept carefully. The second conductor, when it is carrying some current, it is observed that the second conductor of length L is in equilibrium. Then 2 things he will ask you. 1, what is the magnitude of current that is passing through B? And second, what is the direction in which the current is passing there? So parallel straight conductors means need not be like this only. He can even ask a question this way. First and foremost, if I consider the mass of the second conductor as m, then you can all guess now its weight will be acting downward. Due to that weight, officially speaking, the second conductor should fall down. But it is not falling. He said it is in equilibrium. That means what is the conclusion you can have? There must be an equal force to that of weight which is acting upwards on the same conductor. What must be that force here? That force must be the force of attraction between these 2 conductors. So when can the conductors attract each other? If the current passing through this one also has the same direction as that of the first one. So if you look at that one, if I1 and I2 are in the same direction, there will be attraction between these two conductors. That force of attraction acting on the second conductor in the upward direction must now be equal to its weight acting in the downward direction. So what is the simple conclusion there you can have? The force of attraction, it is equivalent to its weight. Come on, force of attraction means this formula you can write is equal to m into g. Can't you just estimate what is the current that is passing through this one as I2? So this kind of a problem also you can expect from the same aspect. But here what he is talking, both the wires initially are given. Initially both are carrying currents he has given. Everything direct, ready-made like. We just have to apply the formula and get the result. But here nothing of that kind. Only one current will be given. Of the second conductor, mass of the conductor will be provided to us. Its length is going to be provided to us. What is the amount of current that is passing through? He'll ask. And in which direction it is passing through? He'll ask. So you have to calculate I2 along with its direction as well. So this model also you can expect from the same kind of parallel straight current carrying conductors concept as such. That of course has not been asked here, but just like that I gave you, this is one more model based on the same one has to remember. This is problem number 18 actually, for which the correct answer is B. Already we have got that one earlier. Now check the problem number 19, which also has been one of the screening questions. IIT screening in 2001, they have given the same problem. Two particles A and B of masses MA and MB respectively, having the same charge, are moving in a plane. A uniform magnetic field exists perpendicular to this plane. The speeds of the particles are VA and VB respectively, and the trajectories are shown in the figure. Then what are the four options given? MAVA is less than MBVB. So simply speaking, momentum of the first particle is less than momentum of the second particle. Check the second option. Momentum of the first particle is greater than the momentum of the second particle. Come down to the third. Mass of the first particle is less than mass of the second particle, and velocity of the first particle also is less than velocity of the second particle. That means MA is less than MB and VA is less than VB. What about the fourth? MA and MB are equal and VA and VB are equal. Their masses are equal and velocities are also equal. That means their momenta are equal, simply speaking. But what he has given over there is a simple figure to show the trajectories in which the two particles are moving. What he said over there, look at, he said first particle is just making this trajectory, second one is just moving along this trajectory. That's what he has mentioned. Both are circular, no doubt. This one is the first one he said, this one the second one he said, but at the same time he has shown the direction of magnetic field like this. Look to the way he has provided the direction of magnetic field. He is just putting all dots like this. So one should understand dots means the direction of magnetic field is normal to the board or paper, but outside the board or the paper. If you put intos over there, the direction of the magnetic field is into the board like, normally inward. Now here normally outward, that is the concept. So what we can understand, this is the first one given and this one is the second one given. And he said the mass of the first one as MA, mass of the second one as MB, velocity of the first one as VA and velocity of the second particle as VB. This is the data provided to us. Now, first and foremost, the moment it is taking a trajectory of circular path like, one should understand centripetal and centrifugal forces acting on those two particles, or individually if you take, on the first particle centripetal and centrifugal forces are acting equally in opposite directions. So, what is the general condition we can write here? B Q V must be equal to mv square by r. This is the centripetal force which has been caused by the applied magnetic field, and this one the centrifugal force, which of course is mv square by r by formula. Now you can cut this v off. Then what can we write now? R is equal to mv by bq. But according to the concept given, he said two particles A and B of masses ma and mb having the same charge. So, charge is constant. They are entering into the same magnetic field. That means magnetic field also is constant. Then what can I conclude here? That implies radius is proportional to m into v. Just look at this equation. Radius of the trajectory is directly proportional to the product of mass of the particle and its velocity. In other terms, it is directly proportional to the momentum of the particle. Now just look at this figure carefully. Which trajectory that is having a greater radius you see now? The radius of the first one is more than the second. So what you can understand from this one? Since RA is greater than RB, what should be my condition then? MA VA must be greater than MB VB. I once again repeat, since the radius of the trajectory of the first particle is greater than the second, I can come to this conclusion, MA VA must be greater than MB VB. So which option that is given like that, you check that. Second option is given that way, MA VA is greater than MB VB. So this particular option is tallied with the second one over there. The answer whatever we have got here, and the second option what has been given there, both are one and the same. So correct answer for this particular question given in 2001 IIT screening paper, that is the second option. So momentum of the first particle is greater than momentum of the second particle. So what is the general conclusion you should have in memory? When magnetic field and charge of the particles are equal, then what can you conclude? Radius of the trajectory is directly proportional to linear momentum of the particle. That's all what we just want. So this is problem number 19 what we have in this order. Check the problem number 20. The magnetic induction at the point O. If the current carrying wire is in the shape shown in the figure. He is giving us a conductor. In what way? Just look at. This is the center. It's now starting from here. And here he just has taken that one like a parallel conductor like. This is the radius there. So what is he talking about? This is point O. This is radius R. This also is radius R. He has mentioned few points like the current is entering this way. Current is going this way. It is now exiting like this. This is the current. And he has just given you this point as A, this point as B. Right? And there are two more points he has given, one as C and one as D here. What is the magnetic induction at this point O? That is a question. Now if you carefully observe here, there are two different conductors you are observing here. One is this AB if you take. Since the point is an extension, it's on the extension of this line, there will be no magnetic field due to this current there. So AB need not be considered. But CD we can consider. What is the value of B with respect to this CD? It's now, you can directly take mu naught by 4 pi I by R into sine 0 plus sine 90. So you can understand this one is 0, therefore you will be getting B as far as the conductor CD that is concerned, mu naught by 4 pi I by R you will be getting. This is regarding the straight conductor. What about this circular conductor now? Let us take that. What is magnetic induction due to the circular conductor AC? You can again write mu naught by 4 pi I by R till that extent common. How much angle it is covering? This angle is known to us as pi by 2. Then the remaining angle certainly will be 3 pi by 2. So you can write 3 pi by 2 whole divided by 2 pi. That means out of 2 pi angle, 3 pi by 2 angle has been covered by the conductor. Now you can cut this pi here. This now becomes mu naught by 4 pi. This is 3I by 4R. So what we can now write? This is B with respect to the conductor AC. That is the second one for us. What is the net value or effective value at B? First and foremost, if you look at the direction by showing right hand thumb, the direction of magnetic field here is coming out. Whereas according to this also, it's coming out. So both the directions are same. Therefore, we have to add both of them. So what will be the value of effective magnetic field now? BCD plus BAC. What we can take common? Mu naught by 4 pi into I by R. You take common. What is left here? It's 1. And what is left over here? It's 3 by 4. That too, in what manner we just have to take up here? This 4 pi also is here. BAC, it's mu naught by 4 pi into I by R into the value of phi. That is, what is the total angle that it is covering? What is that phi over here? It is 3 pi by 2. So if you write this value, how much it will now be? The value is going to be mu naught by 4 pi into I by R into 3 pi by 2 we will be getting. This is BAC. That is the second one. If you add these two, you will be getting 3 pi by 2 plus 1. Look at those options given over here. First option is mu naught I by 4 pi R into 3 pi by 2 plus 1. Second option is mu naught I by 2 pi R into 3 pi by 2 plus 1. Third option is mu naught I by pi R into 3 by 2. Fourth option is mu naught I by 2 pi R into 1 minus 3 pi by 2. Correct answer whatever we have got here is exactly the very first option what has been provided to us in this problem number 20. So we can write directly the answer for this one as A. So this is the way you people have to tackle this model. Only thing you should be perfect with is the application of right hand rule. What is the direction of magnetic field that is produced due to this portion, and what is the direction of magnetic field produced due to this circular portion? If both are in the same direction, add them. If one is opposite to that of the other, take the difference of those two. Out of them also, you need to understand whichever is dominant. The resultant magnetic field will be along that direction only. In this particular case, both the directions are outside the board. Therefore, I can even give the direction like this. It is a dot with a small circle around. That means it gives you that the direction is outside the paper, normal to the surface of it. That is the concept. So this is problem number 20, for which the correct answer is A, that's given there.